In the last video, we created a model which got quite good in deciding whether a ship is depicted in a radar image patch or not. This illustration shows the rough layout of the model, even though it is missing the normalization and dropout layer. We use two blocks of conv2d layers with a max pooling, followed by a flatten layer and a final dense layer. As it is a sequential model, the data is passed from top to bottom in this illustration. So we pass a patch through the model and receive a prediction between 0 and 1. And we will now try to deploy this model on the large radar image showing the Bosporus. To do that, we will implement a sliding window approach. So we start in a corner of the image, like now the top left corner, to pick a 64 by 64 image patch from there. Then we push this patch through the model to receive a prediction. As there are no ships in this patch, the probability should be close to 0. Then we move the window a little bit of, let's say, 32 pixels to extract the next patch and push it through the model. And this is what we are doing over and over again. So we move over the whole image, extract all the patches, push them through the model and hope to get a high probability when a patch with a ship is extracted. Then we save the position of the window to count the ships and highlight it later in the image. So let us implement this with Python. As usual, we take care of the imports first. I already added NumPy and matplotlib, but I will also need the pillow library again to open and manipulate the large radar image scene. So from pill, import image, and image draw. We use the open function from the image class to open the radar image and the image draw class to draw some rectangles into the image at those places where the model indicates a ship. Then we also import TensorFlow.keras.models as models. As models has got a function load model, which we will use to open the h5 file in which we saved our trained model. Now that we have done our imports, we can open the radar image. I will store it in the variable img and open it with image.open and provide the relative folder path, which I have copied. This is currently opened as a pill image, so I can get the size of the image with img.size. With 2711 × 1836 pixels, the image is currently quite large. And as I want to show you how you can draw rectangles into this image, I will downscale it for now. The downscaled version of the image should be stored under the variable img small. Then I take the image, say resize, and provide the target size as a tuple. The size should roughly be a tenth of the original size, so 271 × 184. After that, I also have to remove the alpha channel, which by default comes with a PNG file. If you don't do that, you might get some trouble when plotting without matplotlib. So I add a .convert and specify to turn it into an RGB image only. Then I just call it to be plotted. Now that the image is smaller, we can take a look how to draw a rectangle into it. First, we have to turn the image into a drawable version. Therefore, I call image draw and provide the small version of our image. As we want to define where the rectangle should be drawn, we have to provide the coordinates. I will write them into variable coordinates within a list, and then we need to provide the upper left corner as a tuple, for which I will use the image coordinate 100 and 100. This is the pixel position from the upper left corner in X and Y direction. Then I provide a second tuple for the lower right corner of the rectangle. This time 150 and 150. In the next step, we actually write a rectangle with those coordinates into the image. We get the draw variable, call rectangle on this, provide the coordinates first, then the outline color, for which I will use yellow. And then define the border width of 3 pixels. Then I open the image again and we can see the rectangle that we created. So by providing the upper left and the lower right coordinate, we can easily add a rectangle to the image, which can indicate where a ship was found. What we also need for our sliding window approach is the crop function in order to extract the patches from the large image. Let me also show you this on an example. I want to store the crop version in a variable called imgCrop. Then get our small version of the image and call .crop on that. This time, however, the coordinates are provided as a single tuple, with the coordinates for the upper left corner first and then the lower right corner. As you see, I have chosen coordinates for a slightly larger area than our rectangle that we added before, so this rectangle will also be visible when I plot that cropped patch. If I wanted to pass that patch into the network now, I would have to turn it into an array first. I can simply use np.array to do that. And then I have a simple NumPy array with a shape of width, height, and the channels, which are currently not correct, but we will take care of that later. So let us start with our moving window approach by loading our trained model. I will store the loaded model under the variable model. Then get the models class that we imported from Keras to get the load model function and provide the model's file name. As it lies in the same folder as the script, I don't need a folder path. To check if that is really the correct model, I print the model summary and see that it contains all the layers that we set up. As our model is loaded, we can now program the moving window. First, we should set up some variables with the most important values. There's the size of the patches that we want to extract. Then there is the step size of the window, so how many pixels the window jumps to the next patch. I will set this to 32, so half the patch size. Then we need the width of the large radar image, which I just grabbed from the image size at position 0. And the same for the image height, but at index 1. The code for the moving window that we will write now will not be very efficient, but it will be easy to understand. First, we are going to iterate over the pixels in x direction and do that with a for loop. So for x in range, then we start at position 0, and the maximum values should be the image width. And the interval is the step size. Now I will just print the x values. And you see that we start at 0. Based on that and the known patch size, we could also calculate the lower right bound of the patch and extract the patch from the image with those coordinates. But let me elaborate on an issue that we will encounter with that approach. After we would have extracted the patch, we could use the next x position, which is at 32 pixels, as we have a step size of 32. There we also extract a patch and move to the next position. Repeat the extraction and keep on moving along the x-axis. Eventually we will come to the end of the x-axis and reach a value of 2688. This is the last number in this iteration, as the next step, with 32 additional pixels, is larger than the width of the image, which is 2711. But as this number is just the upper left corner of our patch, and we still have to go 64 pixels into the x and y direction, we would exceed the size of the image. Let us deal with that problem with a simple if statement. If the sum of the current x value and the patch size is larger than the image width, we change the value of x to the width minus the patch size. In other words, if we reach a point with which we would exceed the image, we replace the position by the last possible one that will not exceed it. Now the last value is 2647, and if we add 64 to it, we reach exactly the maximum of the image width. But you can see that we have this position several times now, as our if statement gets triggered not just once. We will solve that issue with a simple trick. After we have extracted the position and have done everything we wanted to do with this information, we will add another if statement. This time with the condition if x is equal to this specific last possible position. We will break the loop and stop it from providing the next value. This time we only get the position 2647 one time. So now we are able to iterate correctly over the x-axis, but our image has 2 dimensions. So we also need to iterate over the y-dimension for each x position in order to move our window over the whole image. I remove this print statement and replace it by nearly the same code as we used for the x-axis, except that I changed the x to y and the width to height. And add the same condition to break the while loop, as the problem applies to this axis as well. Between those 2 conditions, I will now implement the rest of the code. Let us first print each x and y coordinate to see if everything works. And you might notice that we not move our window from left to right, but actually from top to bottom. Now that we have an x and y coordinate, we can use them in combination with a patch size to crop patches from the image. And I want to store the cropped patch in the variable patch. Then take our image and use .crop on that. Now I have to provide the upper left corner of the patch first, which is x and y. And then the lower right corner, which is x plus patch size and y plus patch size. As this patch is currently a pill image, we now have to turn it into an array with the help of NumPy. Then we only want to keep the first channel, just as we did during training. And then reshape the patch with .reshape. To have a dimension for the batch size, for which I use a -1. Then the size of the patch, and a single channel. Now we can push this patch through the model and save the prediction as a variable. We call our model, say .predict, and push the patch through it. Then we want to save all the coordinates where the model is very sure that there is a ship. So we implement another if statement with which we check if the prediction is above a certain threshold. As the prediction is in a nested tensor, we need to access it first and can then compare it to a threshold of, let's say, 99%. If this is the case, we will save the position in a list, which we first have to set up. And then add the coordinates as a tuple to this list. Now we can run this cell and apply the model on our radar image, which will take a couple of minutes in my case. So the processing is done on my machine, and I added a print statement to get the number of detected ships by getting the length of the list where we store the coordinates. In my case, the model suggests that there are 91 ships in the image. But without visually highlighting the patches the model interpreted as a ship, this number is hard to validate. Hence, we should draw all the positions as rectangles into the image. First, I get a copy of the image, as I don't want to manipulate the original one. Then I turn it into an image into which I can draw something, just like we have done it before, with image draw.draw. And now we can iterate over the list of ships. Set up our list of coordinates. And the upper left coordinate is just the tuple of positions itself. And the lower right corner can simply be calculated by the x-coordinate in the position tuple, which is at index 0, plus the patch size of 64 pixels. And the y-coordinate, which is at position 1, plus the patch size. All that is left to do is to draw a rectangle of those positions with img draw.rectangle. Provide the coordinate list, an outline color of yellow, and a width of 3. Now we simply write that image to a file with img copy.save and an appropriate file name. And this is the result of our first object detection model with a moving window. Now let me add 3 more things. First, the time it takes to apply this moving window approach is way too long. But this is not the model's fault, but the way we implemented the moving window. I want to copy some more efficient code that does the same thing, but just in a matter of seconds instead of minutes. The first function creates a tuple of patch images and their coordinates in the image. The second function runs that function and accumulates the patches to a user-defined number of batches. If this number is reached, in my case 32 samples of image patches, all 32 images are run through the model at once. This way we make 32 predictions at a time. The coordinates of patches with more than 99% are stored in a list, which is returned at the end of the function. Then I just call the function, provide all necessary arguments, and draw the coordinates into the image, just as the last time. The fact that some ships have not been detected might be due to the way the moving window moves over the raster. Some ships might have been on the very edge of a patch, as the window was only applied every 32 pixels. The model, however, only got training data where the ships are in the center of the patch, and that might be the reason for some missed ships. The second thing I want to mention, moving window approaches are not very common anymore. Today we have a lot of very advanced object detection models that are more precise and a lot faster. However, they are so complex that they exceed the scope of this basic course. Even though setting them up from scratch by oneself is very hard, using those models is often very simple, and there are a lot of videos about that. Some of the models that are state-of-the-art at the time this video was recorded are YOLO V9, Detectron 2, or Faster RCNN. Sure, those are just a few of them, but they might be a good point to start if you want to dive deeper into object detection. And the last thing I want to mention is that CNNs can not only be used for object detection, they can also be used for different types of segmentation, like semantic segmentation or instant segmentation, which most of the advanced models can do as well, by the way. Or you can translate an image into another domain, like turning land use and land cover data into a satellite image. So CNNs can do a lot of things, and we only scratched the surface.